Good morning. This lesson is for my Honors Integrated 1 class. But before I get started, I want to say I hope everyone is doing all right out there. I don't remember what title this is. Might be lesson 16.1b or 16.2. It doesn't matter. What does matter are our three goals. Our first goal is going to be to review the Pythagorean Theorem and how to use this on the coordinate plane. Our second goal is going to be creation and validation of the midpoint formula on the coordinate plane. And our third goal is going to be discussion of segment addition postulate, coplanar, parallel, and colinear. This last part is kind of forced into this lesson. It doesn't really flow with the first two parts, but I have to talk about it because it's in this section. So it's going to seem a little disjoint. Forgive me for that, but I'll make it work. Anyways, let's go ahead and jump into our first goal. Review of the Pythagorean Theorem. It is an equation used on right triangles. Here's an example of a right triangle. A side length of A, a side length of B, and a side length of C. And the equation for this is A squared plus B squared equals C squared. Now, I want to point a couple things out. C is a hypotenuse length. Now, the hypotenuse is the longest side. And notice that in the equation, the hypotenuse is by itself. A and B, these are called the legs. And the legs make the right angle. They're the shorter two sides. All right, so the length of the leg squared plus the length of the leg squared is equal to the length of the hypotenuse squared. Now, many people don't realize this about the Pythagorean theorem, and I'm going to read this because I keep repeating myself, but the equation is actually about the squares that are made off the side lengths of a right triangle. The square off the hypotenuse is the same size as the squares off the legs. An example of this is a right triangle with side lengths 3, 4, 5. Remember, 5 must be the hypotenuse because it's the longest, the side length. So I'm going to verify that this is the side length of a right triangle. So I know that the length of 3 squared plus the length of 4 squared should equal the length of 5 squared. I get 3 squared is 9, plus 4 squared is 16, and 5 squared is 25. 9 and 16, that does get me to 25, and that verifies that these are the side lengths of a right triangle. Now, I want to draw the picture that shows what I'm talking about, the squares off the side lengths. So, give me a second while I draw this here. I'm going to try my best to make it fit with what I have left on the whiteboard here. All right. So, I'll call this side length 4, this side length 3, not 5, not because it's not the hypotenuse, and this side length 5. So off the side length 4, I'm going to make a square that has length 4 by 4. So if I drop this down and make it the same length, and come over like this, and I cut this up so it has 4 equal columns and 4 equal rows. This is a square off the side length of 4 that has 16 little squares. If I come off this side length of 3 and make a square with length 3 by 3, see if I can do this one. There we go. And I come down like this. Then the square off of the side length of 3, the 3 by 3 square has 9 little squares. So I have 16 little squares off my side length of 4, 9 little squares off my side length of 3, and off of 5, let's see if I can draw this. Oh, air ball. There we go. That's a little bit better. All right, and off of this, I have a 5 by 5 square. Is that right? 1, 2, 3, 4, 5, and then so off my hypotenuse, I have 25 little squares. And remember, off this leg I have 16 little squares, and off this leg I have 9 little squares. So in fact, the equation itself is about how many, is about the squares off the legs adding up to the square off the hypotenuse. This always works for every right triangle. And I kind of think that somehow, some way in our history, someone looked at squares and put them together and realized they could actually make a right triangle out of it. And that might be how they discovered the Pythagorean Theorem. So when we move on to the second part of this goal, how to use this on the coordinate plane, what we're actually going to be looking for is we're going to try to figure out how to find the side length of a square. All right, so I'm going to go ahead, erase this, or I'm going to hit pause, erase this, and I'll be back. I'm back for the second part of the first goal. So let's go ahead and move into that. Now, before I go any further with this first goal, I would like to spend a couple minutes reviewing how to solve equations with a squared with the unknown. So it might be a c squared we don't know, an x squared we don't know, but I'd like to go over how to solve this. So if you get to a point where it says x squared is equal to 9, the way that we're going to solve this is we're going to square root both sides. So I'm going to square root x squared, and I'm going to square root 9. All right, square roots and squares cancel each other out, and we're going to be left with x equals to 9. The square root of 9 is 3. So what this is actually saying is I want the side length of a square with 9 small squares. All right. Another way to look at this would be instead of square rooting x squared, we could look at it as x times x equals 9. What number times itself is equal to 9? And that would be 3. 3 times itself is equal to 9. Now, -3 and -3 also equal to 9, but in the case of today's lesson where we're finding length, we don't talk about negative length, so we throw out the negative answer. But again, the square root of 9 is 3, and that's what we get. Now, if we get a problem that looks like this, x squared is equal to 15, and we square root both sides, and the square root of x squared is x. I don't know what the square root of 15 is. It's okay to leave it as the square root of 15. Okay? If you don't know what the square root is, just leave it. And remember, we don't necessarily know a nice number that multiplies by itself to get 15. I know a nice number that multiplies by itself to get 16. And I know a nice number that multiplies by itself to get 9. So maybe the number we're looking for is somewhere between the nice number that multiplies by itself to get 9 and the nice number that multiplies by itself to get 16. Okay, now that we have the skill set in solving equations with a square by using a square root, we can now move on to the point of this first goal, and that's how to use the Pythagorean Theorem on the coordinate plane. So the key idea is we use the Pythagorean Theorem to find diagonal length. We don't know how to count diagonally. Consider the points 1, 1, and 5, 6. How far apart are they? Well, 1, 1 would be right here. Excuse me. And 5, 6 would be right here. I do not know how to count diagonally, so I can't do that. However, we can make a right triangle out of this situation. Okay, and let me redraw this again. So there's my 1, 1. There's my 5, 6. I'm going to connect these. I'm going to draw a line straight over until it's underneath that point, and I'm going to draw a line straight down. Or straight up. I made a right triangle out of this situation. I can find out my horizontal length. I can count horizontally. So from here to here, from 1 to 5, I need to go 4. 1, 2, 3, 4. And to go from 1 to 6, I have to go 5, right? 1, 2, 3, 4, 5. So I'm able to find the legs on my right triangle, which means I need to find the hypotenuse. So this is my unknown. So my equation now becomes 4 squared plus 5 squared is equal to x squared. 4 squared gets me to 16. 5 squared gets me to 25, and x squared stays as x squared. 16 and 25 is going to get me to 41, and 41 is equal to x squared. Now, just like I did over there, I'm going to square root both sides. And the side length of my hypotenuse, once I remove the square off of the x squared, is going to be the square root of 41. That's how long this is. So the unknown side length is square root of 41. And I'm going to check off my first goal because that's how I use the Pythagorean Theorem on the coordinate plane. I use it to count diagonally. So I'm going to go ahead and erase everything and come back with the second goal. I'll be back. I'm back. All right, we're talking about our second goal today, and that's creation and validation of the midpoint formula on the coordinate plane. So I'm going to try teaching this a little different than I have in years past. I want to connect some ideas that I've used and see if that helps us get a better understanding of what we're doing here. So starting off our second goal, let's talk about the definition of a midpoint. A midpoint of a segment is a point that is on the segment and is equal distance from the endpoint. I have to say this on the segment because there's points that are the same distance from endpoints that aren't on the segment. That's a later idea. And I also want to review with you the transitive property. If A is equal to C and B is equal to C, then A is equal to B. Now remember, if two things are equal to the same thing, then those two things themselves must be equal. A and B are sides of the equation. C is also a side of the equation, okay? And I'm going to get the transitive property out of this example, and it's going to allow me to show that the point is in fact the same distance from the endpoints. So our example we're going to work on is we're going to find the midpoint of the segment with endpoints 1, 1 and 5, 3. Our goal here is to make two right triangles with the same leg length. If I'm able to do that, I've gotten to this, and that'll force the point to be equal distant from the endpoint. And by the way, equidistant, I think it's equa with an I. Equidistant. That means that it's the same distance. It's a real fancy way to say the same distance. Where did I hide my marker for myself? There you are. There you are. Okay. So I'm gonna graph these here. I'm gonna draw a nice large graph. So hopefully we can see the ordered pairs very clearly. 1, 2, 3, 4, and 5, and 1, 2, 3, 4, and 5. So I want to go from 1, 1 to 5, 3. 1, 1 to 5, 3 right here. Okay, that looks about right. And so I want to find the point that is the same distance from the endpoints. Okay? And so what I'm going to do is I'm going to figure out how far horizontally I need to go. So to go from this endpoint to this endpoint, I have to go 1, 2, 3, 4. Right? So what that means is I can go horizontally a length of 2. Let me do that from here. Horizontally a length of 2. Because again, horizontally the whole length is 4. If I cut that in half, I go a length of 2. Now to go vertically from 1 to 3, I have to go a height of 2. So if I cut that in half, I'm rising at a height of 1. And again, I'm rising at a height of 1. So what I've done here is I've created two little right triangles. And I am going to claim that this is the midpoint. And so I'd like to argue that it is, in fact, the midpoint. So I'm going to call this length 1 from this point to this point, and I'm going to call this length 2 from that point to the other end point. All right, so I can find the length of the measurement of length 1 because I can use the Pythagorean theorem. I can count diagonally, right? So I can actually count diagonally, and I would get, let's see here, length 1 squared is equal to my legs, the length of my legs squared. So it's going to be 2 squared plus 1 squared. And the length of length 2, I'm sorry, in the Pythagorean theorem, length 2 squared is equal to 2 squared plus 1 squared. Now, I've created the transitive property using the Pythagorean theorem. I have two things equal to the same thing. Length 1 squared and length 2 squared are both equal to 2 squared plus 1 squared. So what that means is length 1 squared is equal to length 2 squared. And if I square root both sides, I get the fact that length 1 must be equal to length 2. So I know how to find the midpoint. Now let's actually find the coordinates of the midpoint, and let's see if we can realize how we get the coordinates from our endpoints. And if we're able to do that, we're able to create our midpoint formula. All right, starting at 1, 1. If I go over 2, so I'm adding to my x, and I go up 1, that means, let's see, I'm adding to my y, so that means that I would have a 3 and a 2. And again, if I go over 2, that's adding to my x, so I'd have a 5, and I go up 1, that's adding to my y, I'd have a 3, and I would get to my other endpoint, 5, 3. So my midpoint is 3, 2. I know it's my midpoint because I verified it using the transitive property. So my midpoint is 3, 2. And so the question becomes, how do I get a 3 from a 1 and a 5? How do I get a 2 from a 1 and a 4? So maybe pause the video here and try and think how you can use these two numbers to create a 3 and how you can use these two numbers to create a 2. All right, so I'm hoping that you took a couple of seconds to think about how you could have got those answers, and I'll tell you right now. The way that we get a 3 from a 1 and 5 is we add them together and we divide it by 2. We averaged it. We found the middle distance. The way that I get a 2 from a 1 and a 3 is I add them together, 1 plus 3, and I divide it by 2. All right? So the midpoint is actually a formula, and let me explain what it is. We add together the x terms, and we divide it by 2. We add together the y terms, and we divide it by 2. This is the midpoint formula. This is how we calculate the midpoint formula, and we know that it works because of the Pythagorean theorem, okay, and the transitive property. So this is a midpoint formula. I hope that this makes sense. At the very least, you can always just plug numbers in to this formula. We can call this one x1, y1, and we can call this one x2, y2, and we plug it in, and we average them out. We find how far over horizontally is the middle point and how far up vertically is the middle point, and that's our midpoint. So hopefully this makes sense. Now, there will be variations of this question. Maybe you know a midpoint and an endpoint, and so the question is going to be, how do you find the other endpoint? So somehow, some way, this skill set that we have is enough for you to go from a midpoint and an endpoint to find the other endpoint. So you might need to do something like this to figure it out. So hopefully that helps. I'm going to go ahead and hit pause and erase the board and come back and talk about the third goal, which is discussion of segment, addition, postulate, coplanar, parallel, and colinear. So I'll erase everything and I'll be back. I'm back. All right, let's go ahead and jump into our third goal, and it's discussion of segment, addition, postulate, which I'm actually going to do on the next take. coplanar, parallel, colinear, and I actually define postulate, and I'm also going to define one more definition, which we'll see in the last of the next take. But let's go ahead and jump right in. A postulate is a concept you accept as true. When we see the segment addition postulate, you'll see why we accept it as true. Coplanar, what that means is when geometric objects share the same plane. So I drew a plane. This is plane M. Line BC, point A, and point D are on plane M. So line BC, point A, and D are coplanar. However, line DE, because it's dashed, that means it's behind the object. Because it's going through the plane, DE is not coplanar with these guys. But point D is on the plane, so it's that part of the line is coplanar. Parallel lines. Now, actually, before I jump into this, you're going to see new concepts described by recently taught concepts. And this is a really good example of that. Because in order to describe parallel lines, I need to talk about coplanar. Because lines that intersect, lines that don't intersect don't have to be coplanar. Like, you can have non-intersection where they're going in different directions. But that's not what we need for parallel lines. They're coplanar and do not intersect. So both lines are on this plane. This is plane N. And line IJ and line GH do not intersect. This is the symbol for parallel that tells me that they're parallel. You could also write it like this. Line GH, remember we need the arrows above the G and the H, is parallel, that's that symbol, parallel is that symbol, to line IG. All right, let's move on to the last definition for this part. Colinear are, not and, colinear are points. Let me fix this. It's still early in the morning. Colinear are points, segments, and rays that share the same line. An example, I have a line, and there's a lot of coplanar objects on this line. Point K, point L, point M, ray K through M, ray L through M. They're different because they have different starting points. Okay? Where am I? Ray MK, so start at M and go through K. Ray LK, they say MK, yeah. Ray LK, start at L and go through K. Segment KL, start at K, end at L. Segment KM, start at K, end at M. Segment LM, all of these are colinear because they share the same line. They all share a line, KM or LM or MK. So I'm going to go ahead and erase all this and set up the last part of the lesson, I promise, and I'll be back. I'm back for the last time, I promise. So let's finish our third goal here, and I have two more things I want to define. I left out congruent segments in the goals, and I need to define it, so I'm sorry to add this, but it's really important that we do define it. Congruent segments are segments with equal length. Okay, so remember, segments have endpoints so they can be measured, and sometimes segments have the same length, and when they have the same length, we call them congruent. So I have an example of this. Point R is the midpoint of segment ST. Now, I'm telling you something without specifically saying it. When I use the word midpoint, I'm telling you that segment ST got cut in half. That's how I say that. And I say it without, directly saying it. So you're going to see that we talk in code and geometry, and we give you clues. So that word right there is a clue that the length from S to R is the same as the length from R to T. Now, I want to tell you what this mark right here and this mark right here means. That's the symbol that we use for congruent. Now, I'm going to wait to write that down because I don't want to write the whole word. I want to use the symbol for congruent. Now, because I know that the length from SR, from length to S, from the length from point S to R is the same as the length from R to T, I can make two comments. I can say this equation, or I can say this congruent statement. Now notice I don't have a line or a segment mark above this. When I leave that out, I'm talking specifically about the length. That's how I communicate that to you, that I'm talking about the length. And this equation translates into the following. The length of segment SR is equal to the length of segment RT. Or I can say that segment SR is congruent to segment RT. Now this right here is the symbol for congruent. So let's circle that and then associate it with this word. This is the symbol for congruent. That little mark on top of the equal sign, that's called a tilde. And that means the same shape. So this symbol literally means same shape, equal size. Okay? Now, these marks up here, that's how I show you in a picture that segments are congruent. So when you see a mark like this is how we show in a picture congruence. And again, I wanted to wait to explain what that symbol was so I didn't have to write out this long word. We're going to start to communicate with symbols. So remember, this symbol means same shape, equal size. Right? Maybe we should write that down. The top part means same shape. Oh, let's do this. This means same shape. And this means equal size. Okay. So let's move on to the last part of this lesson. And it's the segment addition postulate. If point B is between point A and C on segment AC, then I'm going to translate this as I read it. The length of segment AB plus the length of segment BC is equal to the length of segment AC. And I wrote it out as a sentence. You're probably going to just say AB plus BC equals AC. You're missing out on what it actually means. The length from point A to point B, or segment AB, plus the length from point B to C, or the length of segment BC, add up together to be the length of segment AC. Now, this is a postulate because we accept it as true. You really don't need to argue. You can look at it like, yeah, from here to here plus here to here is from there to there. It makes sense. We don't need to prove it. It's the opposite of undefined. It's so defined we all agree. Okay, now you're gonna set up equations for this, right? So maybe you have something that looks like this. This, and then this would be and then you could say something like this. So you could literally write the equation for this. So where's my marker? There's a marker. I could write my segment addition postulate out like this. And then I can substitute in the lengths. From A to B, it's x. From B to C, it's 2x plus 6. And from A to C, it's 12. And then we go about solving it as we normally would. So I'm going to go ahead and end the video here. Again, I hope everyone is doing all right out there. Have a good day, everybody. Bye-bye.